Friends, first of all, let me thank the Academy for hosting my visit to Poland this time. This is my third visit. The first time was in 1962, which is 50 years ago. The second time was in 1991, and now it is this year, 50 years since my first visit of Poland. And I must say that I enjoyed all of those visits, including this one, and look forward to a few more days in Warsaw, which I have still to visit. There is a conference there. I feel that if I stand, I might block the view of the screen for some people, so I would sit down and talk if you don't mind. And, and what I want to talk about is my recent work on alternative cosmologies. Now let me explain the background to the general audience that if you ask any astronomer or scientist today what is the theory of the universe, he will almost inevitably come with the conclusion, with the answer that it is the standard Big Bang cosmology. So it has become more or less an accepted paradigm for understanding what goes on in the universe. But there are some of us who differ from this majority view. We feel that there are enough question marks in the universe, there are enough question marks in the standard cosmology, and they require us to think in a more different way than what is normally considered standard routine. So I will start with the background as to motivation, why we do this, what is the purpose of this exercise. So to go back to 1990, some of us, the names are written underneath: Arp, Burbidge, Hoyle, myself and Vikrama Singh. Excuse me, my throat is sometimes giving me problem in this trip, but hope you will bear with me. So we met together in Cardiff in 1989, and we had a long series of discussions on cosmology, as a result of which we wrote a paper in Nature which was essentially a critique of the standard Big Bang cosmology. The paper, as you see, is given, the reference is there, and it was called The Extragalactic Universe, an Alternative View. So what we tried to do was to ask this question, why the SBBC is standard Big Bang cosmology. It is the standard version of cosmology. Why it is not the final answer in cosmology. Why there are enough doubts or questions. So this is what we wanted to raise. And it can be argued that there are several unsatisfactory features of the standard models, and we give you a list here. The list can be longer, but I have taken a few important items. First of all, this cosmology starts with a space-time singularity. That means the space-time from which the Big Bang is supposed to have occurred, that space-time has got a singular state, that means it cannot be described mathematically or physically. Then there is very often the age problem, that is, you look at an object and ask how old is it. That age must be less than the age of the universe, otherwise there is a problem. So this problem has not completely gone away. There are still some examples where you see galaxies or stars older than what is considered to be the universe. Then there are too many epicycles. Now for a country which had Copernicus, I don't need to describe what epicycle is. So as you know, there were several assumptions made by the Greeks to prop up the geocentric theory. In the same way, we feel that several assumptions are being made by the standard Big Bang cosmologists to prop up their theory. So you start with if you go on the left hand side, so on the left hand side you start with FRW, which is the Friedman-Robertson-Walker model, without the lambda term. Then people realize that they need the lambda term, so there is this omega lambda in the next circle. Then when they started forming structures, they required n-body simulations, and those n-body simulations brought their own conditions. Then there were things like dark matter, how much of it is non-baryonic, how much of it is baryonic, how much is warm, dark, warm or cold. All these have to be adjusted in order to make the answer come out right. Then we come to inflation. This has been considered an article of faith, that inflation must have occurred somewhere close to when the grand unification had happened between various interactions, and we still don't know what the primary theory of inflation is. People use a kind of ad hoc version of inflation. Each one has his own parameters to put in. So all these problems are still there. And then finally, if you go to the very last one on top, says quantum fluctuations. That means you need to know how the initial fluctuations which led to structures in the universe, they were generated in a quantum gravity world. And as you know, we still are short of a theory of quantum gravity. So you see that there are a whole range of questions which answers are still not obtained, and it therefore is quite okay, we feel, that you should think of some alternative ideas in order to compete with what the standard cosmology is giving. So the other point that I wanted to make is that when you look at the very early universe, you find that there is a speculative nature about it, both observationally and theoretically. Theoretically, that is, if you want to go down to grand unified theories, there is no physical theory yet accepted by high energy physicists which would say this is the grand unified theory we want to apply. So people are kind of guessing or extrapolating. In the same way, astronomers, when they train their telescopes to the very past history of the universe, they want to observe further and further, they hit up a screen which is no longer transparent, that is the screen at the redshift of 1000, and that screen, the last scattering surface according to the standard cosmology, tells you that beyond that there is no coherent observation possible. So you have to again make a guess. So there are both theoretical and observational guesses on which your theory is based. And the final point that we wanted to raise in that Nature paper was that if you look at some of the events that are happening, you find that there are explosive phenomena in the universe where ejections are taking place. And Ambatsumyan, for example, had been very particular in emphasizing the fact that these ejections are very important in determining the behavior of the universe. Now, these lead to very high energy cosmic sources, anomalous redshifts, quantized periodic redshift. There are many events which have been observed by observers but not universally accepted. And one feels that these need to be discussed very carefully because they might contain something very important. So when all this was done, this paper was written in Nature, there was a counter paper criticism written by some supporters of standard Big Bang cosmology, who said that if you don't like the standard cosmology, give us an alternative with which we can compare. Simply criticizing our cosmology is not good enough. So that was a fair criticism. We felt that it was a kind of challenge, putting the ball in our court to play it properly, and we felt that we should evolve an alternative way of looking at the universe, and we wanted to follow the ideas of Victor Ambatsumyan, which I mentioned, whose name I mentioned a little while ago. So what we wanted to do was to take on some of his quotations. So one thing that he said was, one of the important problems confronting us in the study of the outflow of matter and ejections from the nuclei of galaxies is the quantitative evolution of ejected masses. This refers equally to all galaxies, of which the central parts show emission lines, and to the radio galaxies, and to other examples with discrete ejections. So he was emphasizing ejections, and he went on to say that the few facts at our disposal show that these data may conflict with the law of conservation of energy and matter in its present form, and may therefore require a generalization of this law. So what this holy cow that is described here is the law of conservation of energy and momentum, and as you know, in India the cow is considered to be very holy and to be protected, so this law needs to be protected. So what we did was follow Ambatsumyan's ideas and propose a model of cosmology which is driven by those ideas. And this was a paper written by us in the Astrophysical Journal, Fred Hoyle, Jeffrey Burbidge and myself in 1993, and we called this new cosmology Quasi-Steady State Cosmology, to remind us of the steady state cosmology which Bondi, Gould and Hoyle had proposed in 1948. So it was different to be from that cosmology in many significant ways, but it was inspired by the same ideas. So let us see how it goes. So I should mention that since that 1993 paper, we have written several papers in reputed astronomy journals like MNRS, ABJ, Astronomy and Astrophysics, and other journals, as well as in conference proceedings. And in year 2000, Cambridge University Press published a monograph by the three of us on this cosmology, in which we gave all these derivations and results we had obtained till 2000. After that, of course, work has gone on, but this is a landmark, and if somebody wants to know more about this cosmology, he will find it easier to start with this particular book. So the question I now come to is, what is this QSSC, Quasi-Steady State Cosmology? What are its parameters and epicycles? Because every theory has some assumptions, so we would see what assumptions are needed by us. How does it explain the present phenomena of relevance to cosmology? What new predictions does it make that distinguish it from the standard Big Bang cosmology? This is important. So we start with the basic features. So what is the underlying field theory? Just as standard cosmology starts with Einstein's gravity, we had a theory of gravity that originates in Mach's principle and leads to gravitational equations similar to general relativity with the addition of a scalar field. So we had a Machian theory of gravity which gives rise to field equations which are formally written down. Left hand side looks very similar to the Einstein equations, and the right hand side, as TIK is the total energy momentum tensor of matter, and in addition there is a minus F CICK minus 1/4 CLCL GIK. This is a scalar field of negative energy which corresponds to creation of matter. So if you remember, I said that the holy cow of law of conservation of energy and momentum had to be respected. So that is being respected, but with the result that some of the fields taking part in the creation process are negative energy. And we can show that there is no logical problem having negative energy fields, and one can in fact get the right solutions. So the cosmological constant that you get on the left hand side, it comes from Machian origin, Mach's principle. I don't have the time to go into details of these field equations, but I can just summarize that the Mach's principle leads you to relate inertia of matter to the large scale structure of the universe, and a part of that conclusion is that the cosmological constant has got this value of the order of 10 to the minus 56 centimeters to the minus 2. But the important point is that this constant is negative. When I mention negative cosmological constant, people immediately say that then we must be in conflict with the supernova result, where people talk of an accelerating universe. I will come back to that question later. At the moment, let us keep this conclusion in mind. The C field terms arise from inertial contributions at the ends of world lines of particles and describe the dynamics of creation. So the conclusion that the scalar field leads us to is that the typical particle which is created has got Planck mass. Planck mass is a mass made up of the three fundamental constants which are present in the theory, C, H and G, and here there is no other constant involved, so this is the natural mass you would get. And the Planck mass has got something like 10 to the minus 5 grams, and it decays into baryons and photons, and that releases lot of energy. So we call each Planck mass decay as a Planck fireball. So let us look at the creation of matter, the action principle from which this creation of particles happens. The answer is that the condition that must be satisfied at any point of creation where a new particle is created, this left hand side is the square of the Planck mass, and that has to equal the energy density of the C field, which is CL, is the invariant four-dimensional square of the gradient. So this condition, if it is not satisfied, it means that there can't be a creation of particle. So particles can be created only when the strength of the C field is high enough to match the rest mass energy of the created particle. So in general, this condition is of course not satisfied except near compact massive objects. There one has at distance r from mass m the following relationship. So the situation that arises is the following. Imagine that you have a very compact massive object and you've got a distance measured from the center of the object. So at a certain distance you normally have the Schwarzschild radius, what is called the event horizon. If you go further out, then of course the geometrical peculiarities start reducing. Event horizon is a very peculiar state of affairs. Now this condition for the CL, the gradient square, is that as it approaches the event horizon, it shoots up in value. So if you want to create particles, you have to create particles near event horizons of very compact massive objects. So this is what I was saying. So near such a mass, close to the Schwarzschild radius, there is creation of new matter. So when new matter is created, it also creates C field, because both are created together to preserve energy and momentum. So when that happens, the C field has got negative energy, so it repels whatever matter is present, and so it ejects the matter outwards. So you have therefore a explosive creation of matter in the way that Ambatsumi wanted, except that there is no space-time singularity anywhere. We have managed to do this just outside the event horizon. So this creation event we call mini creation event, in which new matter is explosively created, and yet there is no space-time singularity. So one could say that a black hole-like object acts like a creation center. So what we proposed was that the universe is driven by such mini-bangs rather than by a singular, once only Big Bang. So instead of a Big Bang with singularity, we are now replacing them by Batsumian type mini creation events where matter is created but there is no space-time singularity. So let us see how it applies to cosmology. So if you look at the cosmological models, the simplest such model would be the steady state model, in which matter is continuously created homogeneously everywhere, and the universe would expand with a scale factor e to the power t over p. So this is a kind of de Sitter type expansion. However, a more realistic model has the universe expanding with a long-term steady-state scale factor together with an oscillatory mode in which the universe has alternative phases of expansion and contraction. So what happens is you have an expansion which is e to the t over p excuse me, plus oscillations which come because of the following reason. First, you have the expansion in the oscillatory phase, which leads to dilution of C field, and when the dilution of C field occurs because of expansion, the creation activity is switched off in most events, because this creation activity requires the C field to be raised to a given height, and if the C field has fallen down in a level, it cannot be raised to a sufficient height, and so the expansion leads to less and less creation. But at some stage the negative lambda leads to the contraction, because the universe is proportional to distance. I mean, the force of repulsion, attraction is proportional to distance, and this leads to contraction. So when contraction occurs, the C field gets strengthened because of compression and creation becomes more effective. That means the creation centers become more active, and so more matter is being created, and contraction slows down because of repulsion of C field, and a bounce occurs. So you have this opposite feedback every time you either expand or contract. So this process goes on both ways. So the universe therefore has a scale factor like this. First factor is e to the t over p, which is the steady state type of de Sitter factor, multiplied by 1 plus eta cos 2 pi t over q, where eta is less than 1, so that this factor is always positive, non-zero, and q is the period for each oscillation. So what does it look like? Let us see. This is the scale factor. You can see that it goes on steadily expanding as e to the t over p, but also the q is the period over which one oscillation occurs. So you can imagine that at the beginning of each oscillation you have new matter being created, new stars are born, the stars are born, they burn out, and the second cycle then starts again, and the period that we have assigned is 50 giga-year for one period q and 1000 giga-year for the long-term exponential expansion. And what you see as a dot or towards the right hand side, that is where we presently are located. So we see the universe as expanding, but if we see far enough we should be able to see it as contracting also, and I will come to this aspect later. So these are the numbers that we are putting in as representative. So when you compare with observation, first of all, the mini creation events are described by such events as gamma ray bursts, radio jets, active galactic nuclei, then even clusters which are expanding. Ambassumian felt they were not virialized, they are not in equilibrium, so they are also result of initial mini bangs. And we also ran a toy model of the following kind. We took a distribution of uniform points, uniform distribution of points in a given cube. Something like 1 million points were put in, and the cube was sliced to get two-dimensional aspects. But one can always look at the three-dimensional form also. But what you do is, you imagine that initially all galaxies were uniformly distributed. Then you take a certain fraction where new matter is being created which forms new galaxies. So when you have this new point coming in neighborhood of one of the original points, it doesn't happen for all points but only select few, because this phenomenon is relatively rare. So when you do this, you expand the cube because the universe is expanding. Then you ask the question, if I take the inner cube of the same size as original and do the same process again of creating new particle near existing one, and then expanding, then creating, you will go on making a new generation of points. And it turns out that these points begin to develop super clusters and voids, that is the holes and stronger dense point. And if we do the 2-point correlation functions, we get the slope of minus 1.8 numerically. Why this happens, we have not yet managed to work out analytically, but this is what the computer is giving us very simply. So the next question that I want to ask is this cosmic microwave background radiation. Where does this radiation come from in the present cycle, present model? Because we are so accustomed to use of the Big Bang and the very early hot universe to make microwave background that this question always comes. Now imagine that we had all those stars which were born in previous cycles and burnt out. There are infinite number of those cycles. So all those stars will have relic starlight. And what will happen to that starlight today? So the answer is, if you thermalize that starlight, the calculation shows that you will get a temperature of 2.7 K, which means you are getting essentially the presently observed temperature of microwave background, provided you are able to thermalize the relic starlight. So the question is, how do you thermalize it? So the answer is that when you talk of supernovae exploding and ejecting metals which are made by them, those metallic vapors condense not as spherical balls but as whiskers. This has been observationally found in laboratory. So if you take whiskers and ask how these whiskers interact with light, you find that typical length being of the order of millimeter, as you see here, they will thermalize very effectively any radiation that falls on them and emit it mostly in microwaves. So this thermalization is achieved by this kind of grains, and the dust density has the magnitude of the order of 10 to the minus 35 to minus 34 grams per centimeter cube. That is sufficient to cause thermalization. And if you look at all the previous cycles, relic starlight, it's completely homogenized by the time it reaches us, except the very last cycle, because that has been the nearest one. It hasn't had time to homogenize yet. So you will get fluctuations from homogeneity, and if you do the power spectrum analysis, you get a curve which is shown here. The red and blue are the QSSE and Big Bang cosmology. So you see that they agree most of it, but the explanation is different for both the models. For example, the first peak, the tallest peak, which is called the boomerang peak, comes in our cosmology from the fact that if you take the last cycle clusters of galaxies, those clusters will show some non-uniformity, and if you take the typical angle subtended by those clusters at us, you will find that they correspond to this power spectrum peak. So we are able to understand the boomerang peak in a completely different way, and the later peaks are explained in terms of smaller inhomogeneities, like instead of clusters of galaxies you have individual groups of galaxies or simple galaxies. So you will get smaller and smaller peaks. Then the supernovae radiation that I mentioned, where does the supernova, why are high redshift supernovae weaker in emission? Why do they look dim? So the answer in our case is simple, that we have already required whiskers in intergalactic dust, and that those whiskers will also dim the supernovae which are present all over in this universe. So what you require is, therefore, is to ask how much whisker dust can you tolerate. If you have too much whisker dust, then the supernova will be completely wiped out. If you have very little whisker dust, then you won't see this dimming effect. So you can ask this question irrespective of anything else, that let us optimize and get the best agreement to the observations. You will get that way a density of whisker dust, and it turns out to be the same density that we needed for microwave background thermalization. So you get an independent check on the model, because two different sort of restrictions are giving us the same answer. This is what here I have said here. Taking the dust density as a free parameter, one can work out the best fit curve to the data. One gets a fit comparable to the best fit Big Bang model for a density that is consistent with the density required for CMBR thermalization. So we get two different tests agreeing with each other. Then we had looked at gravitational waves. We find that the mini creation events generate gravitational waves if they are anisotropic, and LIGO type observations might be able to just about detect them, although they don't occur in the peak of that magnitude. So, and also if gravitational wave background is computed from all these mini creation events, it is somewhat different in terms of frequency and the spectrum compared to the inflationary background. So it is possible to decide in future a situation where gravitational waves are being caused by inflation or by mini creation events. This is a paper written by several of us in the monthly notices about 5-6 years ago. So now I come to the last bit, that what tests can distinguish, first of all, high redshift objects. The QSSE does not encourage objects of very high redshift, say like redshift of 20 or 30, because the what you call the minimum size of the oscillation is fairly high. So if you find the redshift much greater than 10, then you will have some problem for QSSC. Then absence of dark matter. If we found that dark matter is nearly absent, which is not of course the case, but if it is not there, then there will be problem for QSSC, because QSSC requires an overall density which is greater than omega equal to 1. So it requires lot of matter, and if it's not visible, it has to be dark. But it need not be non-baryonic, it can be any matter. Then this is lack of optical depth of millimeter waves. If we see quasars which show millimeter radiation, some quasars might show that, in which case you will have problem for QSSC, because the dust, this viscous dust is supposed to block out all the millimeter wavelength. The high redshift supernova I mentioned. Now let me go to observations of blue shift. There are some, if you go look far back in time, you will see some objects with blue shift, and the blue shift will be very small, of the order of 0.1, but they are still of interest, because in the Big Bang cosmology there is no scope of seeing any blue shift. And finally, the observations of old stars. If we find stars which are older than 20 giga-years, then we will have shown the Big Bang to be inadequate age, how to have inadequate age to accommodate all matter. Now we did do an exercise from Hubble archival data, and you see here the HR diagram in which stars are moving towards the right. Now those which are pale green line, there are reddish stars. We thought those reddish stars will have about 0.7 solar mass, and if they are already become giants, they must be fairly old, and we estimated their age as 20 giga-year, and this seemed to be going against the standard Big Bang age of 13 to 14 giga-years. But there was a possibility that there is a contamination by dust which may make these positions doubtful. So we are still in the process of looking for cleaner samples. So my conclusion is that cosmology is still an open subject, and there is need for independent thinking. And lot of cosmologists today are like the flock of geese. They are all going in one direction. It is necessary for some of them to think independently and go in the opposite direction or some third direction. I think I will stop here. Thank you.